Thank you for watching HackTheFile. I'm Michael Lopez, and on today's episode, we're going to be looking at Chapter 11 in the Ethical Hacking book series. Enjoy. All right, so we're back. We're about three quarters into this book, and I'm going to be making a lot of videos of this because I want to hurry up and get through this book. We've been getting into some really interesting things, and it's just getting more interesting by the minute. So let's go ahead and continue where we were. So we're on chapter 11, building and installing Linux rootkits. Technology is nothing. What's important is that you have a faith in people, that they're basically good and smart, and if you give them tools, they'll do wonderful things with them. Steve Jobs. Once a hacker has gained access to a machine, they often want to remain undetected. One way to do this is to install a rootkit. A rootkit replaces parts of the operating system with the attacker's code, which is sort of like pasting a photo of a room over a security camera. For example, a rootkit might replace the operating system function that lists all files with one that lists all files except those the hacker created. Alright, let me read that again. For example, a rootkit might replace the operating system function that lists all the files with one that lists all the files except those the hacker created. Oh, okay, nice. Thus, when an antivirus tool attempts to search for malicious files by reading the file system, it won't find anything suspicious. Yeah, that's how we do it. In this chapter, you'll modify the kernel on your Kali Linux machine by writing a Linux kernel module. Uh-oh. A Linux operating system extension that can be used to create a rootkit. So we're going to have to create a backup of my virtual machine. Then you'll override the operating system's function using a technique called hooking. Let me read that again. A Linux operating system extension that can be used to create a rootkit. Then you'll override the operating system's function using a technique called hooking. We'll use this hooking technique to write a rootkit that stops the system from rebooting and hides malicious files. We'll conclude by using a Metasploit graphical user interface (GUI) called Armitage to scan a machine, exploit a vulnerability, and install rootkit on it. Alright. Writing a Linux kernel module. A common way attackers create rootkits is by exploiting a feature of Linux operating system called kernel modules. This feature allows users to extend the operating system without recompiling or rebooting it. For example, when you connect a web camera to your system, the webcam's installer adds software called driver to the kernel. This driver enables the kernel to interact with your new hardware. The ability to insert and run code directly into the kernel makes kernel modules a great candidate for developing rootkits, which work best when integrated into the kernel. In this section, you'll become familiar with how Linux kernels modules work by writing one yourself and running it on your Kali virtual machine. The module you'll create will log a message whenever you add or remove it. Backing up your Kali Linux virtual machine. So yeah, we gotta back it up. Any coding errors you make in your kernel module could result in kernel crashes. So first create a backup snapshot of your Kali Linux virtual machine so that you can restore it in the event of a crash. Provide instructions. Figure Figure 11.1 provides instructions how to do this. So 2, 3, 4. Okay. Select Kali Linux machine from your list of virtual machines. Let me see. I'm gonna stop running my Kali 2. Okay. Then click Snapshot. I don't see no snapshot. So we're gonna have to do machine. Let's see what we got here. Tools, snapshots. Take a snapshot. Let's call it before kernel tampering. Give your snapshot a name and click OK. Oh, what the fudge? Did it work? Alright, that looked like it worked. Writing the code. The kernel module code differs from the other programs we've covered in this book so far. First, instead of using Python, we'll write our kernel module in C. That's because the Linux kernel is written in C, so kernel modules must also be written in C. Secondly, we won't be able to use the standard C libraries such as Uni, STD, STIO, and stdlib because user space libraries are not available in kernel mode. I'll discuss these two modes in the system calls section of the chapter. Another difference between most programs you may have written and kernel modules is the kernel modules are event driven. This means that instead of running sequentially, the program executes in response to events such as mouse clicks or keyboard interruptions. Kernel modules run in a privileged state, which means that they can access and change anything in the system. I like that. Every kernel module must respond to two events: module in, and module exit. The module init event occurs when you add the module to the kernel, and the module exit event occurs when you remove the module from the kernel. To get started, create a desktop folder called LKM Rootkit and create two empty files, helloc and makefile, by running the following command: touch helloc makefile. So let's go ahead and do that. Um, mm, mm. Let's turn this sucker on. Let's see what. Okay. Let's just get rid of all this stuff and start fresh. Okay, so we're gonna go to here. I'm gonna open terminal here, and we're gonna use the command lines instead of the fast way by just creating a file in this directory because I need to practice. So let's go to touch. Let's see. What did you want us to do? Just to make. Okay. So it wants us to make a directory in here. I already did. And create 2 empty files. So we're gonna look to see. Here's the LMK rootkit directory. We're gonna move into that. So cd LMK. So I had to redo this section, this snip of video, because I forgot to make the directory. So alright, so now we're there, in there. So now we're gonna touch hello.c and make file. Is that what I wanted? Yeah, so 2 files, and we're gonna see what's in here. Hello.c, make file. Alright, that's good. Okay, next copy the following hello C, and what we're gonna do is we're going to cat hello dot C. That's ridiculous. Okay. Is it a cat? Search file. Why isn't that working? It's ridiculous. Right, we're just gonna open it and paste it anyways. So what am I looking for? Element key. This is already just. All right, now let's get this code from our library, and we're just gonna copy and paste, and then we'll see if anything's wrong with it. Hello, Colonel reporting for duty. Right, save, close. There you go. That's probably because there was nothing in it. So when I opened it, there was nothing in it. That makes sense. Would have had to have paste or something in it, but okay. So that looks good. Um, remember I pulled that from the code, chapter codes, instead of like copying it from the book. They have it on here, but remember this stuff has errors sometimes because it's man put in, and so just make sure your code is correct. Look at it. Sometimes it doesn't run right. All right. Notice that there is no main method in this program. Oh, instead, we define the function that runs in response to the module int event, which calls the print k function. Print k kern notice hello. Unlike a traditional user level printf method that prints to the console, remember that we don't have a console when running the kernel. The print k method logs the value, each log entry associated with a log level flag. For example, kern notice. Kern notice. Table level 1 lists the various flags and their associated meaning. Next, we define the function to run when the module exit event is fired. Boy, kernel, bye bye. Lastly, we register the function with the kernel limit 5 module init startup. These are the functions that will run when the kernel module is loaded and removed, respectively. The kernel license tag is required for all licensed kernel modules. Module license GPL. In this case, we're using the GNU General Public License GPL. Kernel flag. Kernel emerge. Emergency condition system is probably dead. Kernel alert. Some problem has occurred. Immediate attention is needed. Kernel critical. Critical condition. An error has occurred. Warning. Normal message. Some info. Debug. Information related to program. Now that we've written your kernel module, let's compile it. Compiling and running your kernel module. To make file, you'll create makefile. The makefile you'll create, makefile, will contain instructions the compiler will use to build the kernel module. Open your makefile in your favorite text editor, copy the following, and then save. Let's see if we have the makefile. Reboot blocker, keylogger. We don't. So we're just gonna have to type this in. Alright, let's just type that in. So we'll go here to LMK, rootkit, make file, open that, and we'll just start typing obj-m plus equals hello dot o make dash c. Guess we'll see. Make sure that you have the Linux headers installed. Alright, let's save this and then we're gonna have to come back to this. Alright, we're in the rootkit. Let's just open terminal here. Rootkit directory, and he wants me to sudo app install Linux header uname dash r. Oh, I guess that's probably correct then, if this works. So I guess it is uname dash r. Then run the make command in the lmk rootkit directory to start the build process. So we're in the rootkit. It wants me to put make, and that runs a make file. Missing separator, stop. Okay, uname extra operand IR. So try to build it. What do I do? I put an IR instead of a -R. Gosh. How do I stop this then? Do I quit? Oh, edit. No, view. Oh man, how do I do this? Close. Open with mousepad. Okay. Now we'll come here. That looks good, right? Alright, now we'll come back here and do the same one. Missing separator, make file line 3. Missing separator. Make C. PWD. Let's see if that. Missing separator. Stop. 1 3. Right? Make file 3. Make. Let's see where the separator is. What separator? Oh. See. Modules. Maybe it doesn't need these. Oop. Yeah. Alright, now let's try to run this crap. Okay, it's running. Now let me show you how I fixed this because it didn't run the first time. But it took me a little while to troubleshoot it, and I don't want to make this video really, really long. But you have to have a space here. So the book shows not really good, okay? Nothing. So I had to come here and I had to make it make file Linux kernel. So I copied this, which it is shell uname R. So it is with the parentheses and all that stuff, right? Only thing is, this doesn't show you to put a space between here and stuff. So it's very space orientated for some reason, or maybe not. I don't know. But if you look at my there's a space. So I got it to run obviously by hello.o pilot, then I put a space, all tab. So everything else is right, I just didn't have the space right here, I don't think. But anyways, you gotta mess with this stuff, Google it. So what I did was I took man, my leg fell asleep so bad right now. So I googled how to make make file Linux kernel, and then I just copied and pasted their from there step by step, and it came out okay. That's what I would recommend. I had to cut that process out because it went a little too long, and I don't want, like I said, I don't want to make this video way too long. So there you go. There's your make file. It's running. It did something. All right, now let's look at the next step. All right, next run the following command to insert your Linux kernel module into the kernel. Sudo insmod hello ko. Next run the following command to insert your Linux kernel module into the kernel. So let's move this over. Now he's still in rootkit, so we'll say sudo and mod hello dot kill password. What did that do? Each time you insert the module into the kernel, the Linux operating system will call the dash init function. The module uses print k function to write the message hello. Kernel reporting for duty to the kernel logs, var log, system log, kernel log. Kernel also includes these messages in the kernel ring buffer, which is a circular queue in which the kernel inserts messages it generates. Run the dmessage command to view the messages. So sudo dmessage. As you can see, the kernel ring buffer contains a lot of debugging information. Use the grep command to filter through the results. So sudo, what are we looking at? Dmess grep hello. Hello, kernel reporting for duty. So it worked. So a little make file worked. You can also view the last few messages logged by the kernel using the tail command. So sudo, we've done this in our Linux basics. Sudo this message to d message. And we'll do tail, and that gives us the last few messages, like the most recent messages. Use this, so we'll see the oh, here it is. Yeah, hello, kernel reporting for duty. Loading out of tree module. You can also view the last few messages logged by the kernel using the command tail. Use the ls mod command to view a list of all loaded kernel modules. ls mod. Hello. Yep, there's the one that we loaded. You should find the module you just installed. We saw it. It says hello. You've now successfully inserted code directly into the kernel using a kernel module. This means that you can now modify the kernel, bringing you one step closer to transforming your kernel module into a rootkit. You might be thinking, won't a system administrator be able to discover my rootkit by just listing the kernel modules as we did? Well, yes. But later in this chapter, I'll discuss how to keep your module from showing up on the list. Use the rmmod command to remove your Linux kernel Linux kernel module. So let's remove this. When you remove your kernel module, the operating system will call the exit function and the module will log the bye-bye message. You must be careful when implementing your module. Coding mistakes can cause your module to crash. It will be difficult to remove the module. If this happens, reboot your virtual machine. You can find further details about building Linux kernel modules at. We'll just go on here. And we'll just save that directory. So let's look here. And you guys can, let me go back. And you guys can pause it, follow along, write the book yourself, or you can pause it and follow along. Yes, you can pause it and follow along. This is all the stuff we did. I'm gonna run this command again. This just so I can see the exit out of that code to make sure that that was running good, because I don't want to mess my kernel up. So let's clear this and let's run that sudo dmestil. Yeah, there you go. So it says bye bye. So our C code, this hello C, is working, right? So our C code worked, and it looks good. I mean, I've worked with C before, so I don't think this is gonna throw any errors from, any code errors. I mean, it worked just fine. So that was the easy part. Now the harder part was this make file. So the important thing to remember with the make file is the spacing. This ran the command. I mean, you gotta have the proper, so that's obj-m space that space hello.o, right? I don't think I had that like that. I think and then there was a space between here, and then on line 3, line 4, you had to put a tab. I put a little note in the video, so just to go over again, you have to push tab here, and it turns this. And this, if you Google how to make a make file for Linux kernel, this will have all the copy and paste for you, so you don't get it wrong. But you can pause this and copy this exactly, right? There's a space here, there's a space here, there's space here, and that's a capital C. But make sure there's tabs right here, and that's it, and that should work. Now I ran this about 5-10 times. I had to mess with it, and then I copied and pasted from the internet. So that's how I troubleshot this, is what I Googled this and copied and pasted from the internet, from the AI generator, which is really awesome. And I just typed in, like I said, the current Linux kernel, how to make a Linux kernel make file. That's basically what we're doing. And it had these 3, it had, they were naming this something different, but I mean, that you could change that, right? And so that's how you troubleshoot that. So I could do a quick little, I could show you quickly what I did, right? Just in case, because my show's about troubleshooting and getting everything working from these old books. So, staying true to my roots, right? How to make a Linux kernel, how to make a make file Linux kernel. And this is what I go off of. I love this, Bing AI generation crap. So it says create a make file, start, whatever. And then it says define your build target. And it has this little copy thing right here. I just push that. And I put this on the top line, change that driver name to hello, right? And then I copied this one on the next line, and it spaced it and stuff. So that's how I did it. Okay, and I copied this one on the cleanup. That way, you know your formatting is right. I mean, it's the same formatting, but how it has to be, right? Instead of going through the long errors and missing a space on line 3 and all that. I mean, that takes forever. I mean, sometimes you still don't know, what spacing is talking about. The space here, or the space here, or the space, space here. We don't know what space is talking about. So you might as well copy. I mean, once you deal with all this command line stuff long enough, you can see where it is. Like, I'm sure this has to have a space here, right? But and then you got to compare it with the book. So I troubleshot it for you, but that's how you do it. Okay, that's how you troubleshoot it. Google it. Go to that AI generator, copy and paste. Use your common sense, use your deductive reasoning, and then always refer to the book. Look to the book and see what's different. But it's created. Okay, now let's move on. And the code's obviously working because it says bye bye. All right, let's move on to the next thing. So that's what we learned from that. Uh, Doing all these steps already. So I think that's pretty cool. Like, that you're gonna learn basically all this stuff, but you're gonna learn how to troubleshoot it as well. These books aren't always perfect in their writing. Like I said, this does not tell you anything about spacing. You have to Google that or know that on your own, which um, it does. I don't even think it assumes that you know that. It just doesn't tell you about it at all. And when your program doesn't run, you're spending 4 hours troubleshooting it, which a lot of people give up. But don't give up. Watch my videos, and I'll help you through it. Okay, so now let's keep going for at least an hour or 45 minutes or whatever. But I don't want to make this video like 2 hours long. I just want to make about an hour. Okay, so let's just keep going and see where we end up. Modifying system calls. In this section, we'll look at how you can use kernel modules to create rootkits. In particular, you'll learn how you can use them to hook into system calls. But first, I must discuss what a system call is, how system calls work. To prevent a malicious program from directly modifying the kernel, a computer processor divides the memory into two regions, user space and kernel space. When a user program runs, it uses the user space region of the memory. In contrast, kernel space memory can be accessed only when the processor is running in privilege mode. Switching to privilege mode requires special permissions or privilege levels, which are stored in the last two bits of special register called the code segment, CS register. The processor checks the CS register whenever it fetches data from the protected memory. Intel processors have four privilege levels: 3, 2, 1, and 0. Privilege levels is used by user programs. Privilege levels 2 Privilege level 3 is used by user programs. Privilege levels 2 and 1 are used by driver devices. And privilege level 0 is used by the kernel. Kentucky Fried Chicken. However, in practice, modern systems use only level 0, kernel mode, and level 3, user mode. The processor will only fetch a memory section if the CS register privilege level allows it. Figure 11.2 shows how the CS register manages access to protected sections of memory and helps to force kernel space user space segment. CS register times the Intel processor memory, kernel space, user space. Kernel space versus user space in code segment register. Okay. Activities such as reading a file or accessing the network are considered privileged. Therefore, the code associated with these activities is stored in kernel space. But you might be wondering how user level programs like your browser access the network. Well, the processor provides a special instruction called a system call. This instruction transfers control to the kernel, Kentucky Fried Chicken, which then runs the appropriate function. To understand a program activates one of these system calls. Consider the following program, which opens a file, writes the value 7, and then closes the file. Okay, so I don't think we have to write this, but this is just like a demonstration. So integer main file, ftpr, blah blah blah, temp file w, print, close, return. To understand how a program activates one of these system calls, consider the following program, which opens a file, writes the value 7, fprint 7, and then closes it, fclose. Okay. All three operations, open, write, and close, are privileged. Therefore, they must invoke system calls. To see these calls in action, let's look at a snippet of assembly code associated with these fclose functions. Close, move, system call, CMP. A program must follow these steps by using the system call instruction. During the first step, move, the compiler moves the system call number into the CPU register. In this case, the value 3 represents the close system call. Close moves it. In the second step, the processor executes the system call, and the transfer controls to the kernel. The kernel will use the number stored in the register, EAX register, to index into system call table, which is an array of kernel memory that stores pointers to the kernel. Figure 11.3 shows an illustration of the system call table. Address of system call, read system call table, kernel space, file read code, or write, or open, or close the code. Visualization of that. Okay. When the function associated with the system call completes its place, it places the value returned in the racks, which is the close register, and switches control back to the user program. During the third step, 3, the user program checks the value of the racks. The value tells the user program whenever the kernel function returns an error. Okay. Errors are indicated by -1. If an error occurs, the function completes and returns. If no error occurs, I'm sorry. To see a list of systems calls and their corresponding system call number, look at the unistat64.h or unistd32.h file. Unistd is what I meant to say. Unistat. Your system your system. Use the find command to search the file's root directory and the in name option to perform a case insensitive search. So we want to look at these files apparently. Desktop, rootkit. He's still in rootkit. Find in name. Okay, let's do that. Let's see what's going on. So we're still in rootkit. Let's sudo. We're gonna use the find. And then we're gonna say in in UNISTD 64 .h in name in a name in C defines in name. I don't know why I did put the space there. Okay, so user source Linux header generated. Okay, fine. Run user permission denied. All right, I ran. So I ran that search, and it gave me some listings, and then they gave me this one. So I guess this is the one they wanted me to use. Was the user include Linux blah blah blah. So I typed in cat to read it because that's what they wanted me to do. So now we're on this step. I ran into some VM problems, so I had to redo it. So this is where we're at. So select the option 1, that's the one we selected, which is the library used by the GNU compiler, and use the cat to list the file's contents. That's where we're at now. Notice that this file defines several constants, which store the system call numbers. For example, the nr close constant, number 1, stores system call number 3. These constants allow us to write more readable programs. Instead of using arbitrary integers to index into the system call array. For instance, by writing system call table 3, we can use the predefined constants system call table close. Nice. Hooking system calls. Now that we've discussed system calls, let me see, am I recording yet? And how they work, let's discuss how we could design a rootkit that hooks one. Hooking is a process of overriding an entry in the system called table with a new pointer to the attacker's function. Figure 11.4 shows a visual example of hooking the read system call. Address a system call, hacker's file read code, file read code. The kernel module replaces the read entry in the system call table with a pointer to the hacker's read function. Because your kernel module is part of the kernel, it has access to all of the kernel's memory and its variables. This means that it can access the kernel system call table, which is just an array in memory. Because your kernel module can read and write memory, it can also modify entries in this table or any other part of the kernel you choose. Often, instead of re-implementing the entire read function, an attacker can selectively call the original read function from within their new read function. Doing this allows them to selectively respond to reads. For example, they might choose to modify some reads while allowing others to function normally, or they might block reads from their secret files while allowing other reads to function normally. Hooking the shutdown system call. Let's write a kernel module that will prevent a user from performing a software-based system reboot. Man, I've gotten actually I have gotten a virus. I've been hacked where this was implemented and I couldn't reboot my system. We'll do this by modifying the kernel module you wrote earlier, hello C, to hook the nr reboot system call. Let's begin by finding the address on the system called table in memory. Let's begin by finding the address of the system called table in memory. You can usually get this address using the kernel's call system lookup name function. However, techniques for the location of the system call table will vary depending on the kernel's version. Here I discuss a method tested with Linux kernel version 5.7 running the virtual machine. Copy the following C code to below the include statements in your hello C module. Alright, we're going to stop right here. We'll stop right here, and then in the next video, we're going to do some hooking. This chapter is pretty long. Oh, not that long. And it's got some exercises. Complete these exercises. In the first exercise, you'll write a kernel module called a keylogger that logs everything your user types, including username, passwords. In this second exercise, you'll extend your module that it hides from the list mod. Nice. So we can make a keylogger which I'm not going to do because you guys can run through these exercises. What's the next chapter? Stealing and cracking passwords. See, I want to get to that one. But, we'll finish this chapter up in like 3 videos, I'm thinking. But that's for now. We learned a lot. We learned about, the tail end. This was in the basic Linux videos that I have too. How to use grep. We learned spacing details on, we learned a tremendous amount of stuff in this chapter. I mean, so far in this video, it's awesome. And in the next video, we'll go ahead and learn more about system calls and see how they're going to put all this together. Because this is supposed to be a rootkit, which basically lets you. What did it say that it wanted us to do in this? We can't lose sight of what we're trying to accomplish with all the details. So building and installing Linux rootkits. Once hackers have gained access to the machine, they often want to remain undetected. One way to do this is install a rootkit. So basically, rootkits are so you remain undetected. A rootkit replaces parts of the operating system with an attacker's code, which is sort of like pasting a photo over a security camera. For a room over security. For example, a rootkit might replace the operating system function that lists all files with one that lists the files except those a hacker created. Thus, when an antivirus attempts to search for malicious files. Okay, so basically how I see rootkits they're just basically camouflage, right? When a ninja throws down his smoke ball, to get away or to not be seen, right? Your Harry Potter invisibility cloak, So Linux rootkit is so you don't get detected while you're in a system, right? You can set up a rootkit, um, which is awesome, right? So they never detect you. So this is what this is for. Okay, so let's not lose sight of what this chapter is about. You know, so when we pick up on the next video, we'll pick up right here. And I hope you had fun and learned a lot. I know I did. And I'll see you on the next Hack the File. Enjoy.